Now, I just want to give you one example of the flow-based models, just to give you this idea how we can build such a network, which does, the flow transform, and also it can be inverted. And I just use this Real NVP model. This is kind of, base model, like somewhere in between. And many, more advanced models are essentially extension of this guy. So what is the idea here? They just try to do the flow process in multiple steps. And in each step, they use exactly the same architecture. So there's one architecture, again, repeated after that, and so on, just with different ways, right? And every single of them has this simple architecture that I'm showing here in the next slide. And that has this property that you can easily invert it, right? But the key design challenge here is to somehow make this log of death, this expression, to be somehow simple. So that when you want to compute that, or you want to compute the gradient, you want to do backpropagation, you're going to save lots of computation. This is the key bottleneck in your design. Because if you think of a general invertible model, you can still come up with some model, but then the backpropagation part could be quite hard. So let's just focus on one particular module in Real NVP. So as I told you, this is one module. It means I'm showing here by z and x because I want to keep it consistent with what we had before. But eventually, in practice, you are going to repeat this multiple times, right? So you get your z, you get the first x, then you pass that x through the same architecture, next x, and so on. So this is the unit that you can use to build your network. Now, what we do here, we're going to have, first of all, we're going to get our z, and this z is d-dimensional, right? This guy is d-dimensional. I'm going to cut it into two parts. One part is the first r entries of z. The second part are the remaining d minus r entries, right? Okay, so I just choose one r, any r that I want, and then I just cut this z to two parts, right? One of them is the first r entries. The second part are the remaining entries. Now, I also set two neural networks. So these guys could be simple MLP, whatever you want. And these two neural networks have their own parameters. So the first one is S, which is the scaling network. Scaling network is having some parameters. I'm showing it here y beta. And what does S do? It's going to take one r-dimensional input. It's going to give you d minus r-dimensional output. Okay? So the input to a scaling network is exactly the size of your first part in Z. The output is the size of the second part. Clear? Same thing for T. T is the translation network. So it's going to get, again, one r-dimensional input. It's going to convert it into d minus r-dimensional output. Now, how you compute your output given the input, for the first part of the output, you're going to copy exactly this first r entries into the first part of the output. So the first part of x is exactly the first part of z. Yeah? The first r entries inside x are exactly the first r entries inside z. Everybody's clear? Okay. So for the second part, the first thing that I'm going to do, I'm going to pass the first part of z through the scaling network. So I give r-dimensional input. What's going to come out of this scaling network? What is the dimension of the output? D minus r, right? So I'm going to have d minus r different entries at the output. I get these d minus r different entries. I compute the exponential function of them, and I multiply them with the next d minus r entries, the second part of z, entry-wise. Okay? So every single guy coming out of this network, after being passed through the exponential function, is going to get multiplied with the corresponding entry inside the second part of z. Clear? Now, I'm going to get, again, the first part. I'm going to pass it through the translation network. Again, R dimensional goes inside the translation network, the output is going to be D minus R dimensional, right? Exactly same dimension as the guy we had here after multiplication, right? And then I'm going to add them up entry-wise again to that expression. So T, the translation output, is going to be added to whatever we have computed up to this point, right? This process is going to compute the second D minus R entries inside X. Okay? Everybody's cool? So you got the idea. The first part got copied. Then the second part is going to be first scaled with the first part, then again shifted by the first part again, and then it's going to be copied out at the output, right? And the scaling and the shift are being done by the scaling and translation networks. Okay? And these networks are the guys which you are going to learn, right? The parameters are somewhere here in between. So our model, you can look at this from Z to X as a flow network, and then the parameters of this flow network are essentially whatever you have inside your translation and scaling networks. Okay? Questions? Now, if that guy is clear for you, then this is quite easy to see that this network is easily invertible. Why? Just look at this architecture again. So I have this one, but this time instead of getting from Z to X, I want to get from X to Z, right? If I want to do that, how can I do it? Okay, I start from X. The first R entries inside X are exactly the first R entries inside Z, right? So what can I do? I can copy that X, that first part, into Z, right? So that is quite obvious. Then what about the second part of Z? Well, when I wanted to just make the second part of X, I first scaled Z and then I shifted, right? Now I need to just shift back first exactly with the same translation as I had before, right? And I need to compute the translation, right? But when I wanted to compute the translation, I put the first part of Z into the translation and computed the output. But now I am starting from X. What should I do? I can use the first part of X, right? Because first part of X is exactly the first part of Z, right? Everybody's clear? So if I send the first part of X through the translation or scaling network, I'm going to get exactly the same values as I had in the forward flow, right? Because first part of X and first part of Z are exactly the same thing, right? So I'm going to use this property. I'm going to first pass the first part of X through this translation. This is going to be the translation of X, which is exactly the translation of the first part of Z, right? Because first part of X and first part of Z are the same, right? Now, I subtracted from this second part, so this translation is gone. The only thing that I need to do is to just cancel the scaling. And for that one, again, I can do it quite easy. I send the first part again through the scaling network. I'm going to get the scaling factors. In the previous case, when I was going forward, I just multiplied to exponentials, right? Now I multiply with exponential to minus those scalings, right? And I'm going to get exactly the first part of Z, second part of Z at the output, right? So the key point in this design is that you can get exactly from X to Z with the same operation as you do to get from Z to X. So the inverse and the direct flow, both of them are dual of each other. And they use exactly the same network. And this is very good because this is going to help you a lot in terms of computation. And essentially, whatever you know as like famous flow-based networks, they're always having such an architecture. You always are reserving some part of your input, you copy it at the output, and then you use that one to process the other half. Because this is the only way that you can guarantee you can get back, right? Questions? Yes?
I guess I sort of get how the model works, but I'm wondering, how does this relate to like the stuff we're talking about at the start of the chapter with like the mapping and the cylinder? Like, how is this a lower dimension representation?
Yeah, we are not still doing the lower dimensional, so this Z that you have is still in high dimension, right? So you cannot really think of it as the cylinder and the surface. But what you can think of cylinder, and then you assume that I am taking any point on this cylinder, and then I am compacting it inside a tiny sphere at the center, right? You can still do it, right?
Wait, so the steps that we're doing here are still like, in the same way that the cylinder to the flat plane is something that you can go back and forth from, the z to the x here is another back and forth thing?
Yes, but the point is that, I mean, the thing that you say is right, but the point here is that even though you can get exactly from one 2D point to the 3D point in that example, but if you want to compute a distribution on that, and you want to convert it into the distribution of the cylinder, you are not able to do this, because that normalizing flow is not going to work for you. So still, this is a valid idea, and this is what we're going to do it in, for instance, GAN. Okay? So we start from smaller latent. But then you're going to see that you're going to have a hard time computing the likelihood. So you cannot directly compute the likelihood. You can simply just compute it indirectly. Okay? So somehow related, but at this point we're in the same dimension. So if you want to have visualization of that, you assume that you have the cylinder, but then you're somehow mapping it into a latent space, which is a compact sphere at the center. Still, it is easier to sample from that sphere as compared to the cylinder, right? Because once you have a sphere, as long as you know the radius of that sphere, any point that you shoot inside that region is going to be one valid point, right? Whereas on the cylinder, you need to know exactly the curvature of that two-dimensional surface, right?
I think that makes a bit more sense.
Yeah, okay, that's good. Okay, questions?
Yeah. Just curious, what's the benefit of using this architecture in lieu of just one deep neural network?
Yeah, because this one gives you the inverse. If you just use, yes. Because you really need to have the inverse flow, right? So if you don't have it, you cannot train, right? Yeah. So this somehow guarantees you can make a neural network so that this is invertible under some, advanced design. But then the issue is that, as I showed you before, then you need to compute that log of that, and that could be very computation expensive. No. Questions? No question? Okay. So now, with this real MVP, the very interesting property is the Jacobian of the Jacobian matrix. So if you just write down the Jacobian, it needs a bit of messy calculation, but at the end of the day, you can show that the Jacobian is simply in this form. Okay? Now, let's look at it together. The first part here is a d by d, or sorry, it should be r by r. This is a typo, sorry. I make it r by r. This is I, r by r. It could not be d by d. And this should be also r by d minus r. So I just got confused by r and d here. Okay? So this first I is r by r. So it's exactly the size of your first part, right? And then this is an identity matrix, meaning that its diagonal is 1, anything else is 0, right? Then you're going to have complete zeros here. And then here, in this part, you're going to have d minus r by d minus r matrix. And this d minus r by d minus r matrix is again diagonal. And the entries inside the diagonal of this matrix are exactly the outputs of your scaling network. Okay? And here, you're going to have the gradient of your translation network, or the Jacobian of your translation network, which is going to be d minus r by r, because you have r inputs and d minus r outputs. Okay? Now, you don't really need to understand what is inside this matrix. First question that I have, above the main diagonal of this matrix, what are the entries? All of them are 0. So this means that this is an upper triangle matrix, right? Now, what is the determinant of an upper triangle matrix? If you have an upper triangle matrix, what is the determinant of it? You multiply the diagonal entries. The product of the diagonal entries of one upper diagonal matrix is the determinant, right? So that means that this determinant of the Jacobian, which we said that this is the hard part of the whole computation, that could be easily written in this form, right? Because the first entries, the first R entries here are all 1, so they are doing nothing. And then the remaining diagonal entries are exactly exponential of the scaling network, right? So it's going to be, the determinant is going to be of this form. Now, what's going to happen? I mean, first of all, if I have multiply of lots of exponentials, what's going to happen? It's going to be exponential of summation, right? So I can write it down in the exponential of the sum of the outputs of the scaling network, right? And now, at the end of the day, I need the logarithm of that determinant, right? And if you just want to compute the logarithm of the determinant, that exponential is going to disappear, and it's going to be sum of the outputs of the scaling network, right? So now that guy is very easy to backpropagate over, right? You really don't need to compute that inverse matrix anymore. And you don't really need to backpropagate over the whole Jacobian matrix, because essentially the determinant is quite straightforward, okay? So that being said, if you want to just do gradient, then you basically need to add up everything at the output of your scaling network, and then you compute the backpropagation, which is quite easy thing to do, right? And this is one of the key reasons that they have designed the network specifically in this form, like scaling plus translation and everything entry-wise, right? I mean, you could do it without having entry-wise operations as well. You still get the inverse, but then you're going to get into trouble when you want to compute the Jacobian, okay? So now, there was one other term also that we wanted to just compute the gradient. The term was logarithm of a p function here, the distribution of your prior. If you assume that your prior is standard Gaussian, then log of a standard Gaussian distribution is going to be proportional to the norm of z squared, right? And again, is it a hard thing to backpropagate over this function? No, that is quite easy to backpropagate over this. So computing the gradient is again quite easy. You essentially have the inverse flow. The norm of it is squared, and then you want to compute the gradient. This is again a typical thing that you do in deep learning, so it's not a hard thing to do. You can easily do it. Yeah, this is one example of this real NVP. So this is the data set. I think I mentioned it once in the lecture. So Celeb A, the celebrity 200K celebrity images. And these are the real images coming, the data samples. And then at that particular time, I think it was in 2017 or 18, when it was proposed, this was the output. And this, I mean, for you, the generation of ChatGPT, this is quite funny, right? It's nothing, but I mean, at that particular point of time, it was quite good output. Okay, so that network, if you do it deep enough, it's going to work. Moral of the story, yeah? And it's not hard to train it because of those properties they made in the architecture. Any questions? So everybody's clear? Great. So if you got no question, just a few final notes here. So first of all, this as I told you, this idea of building that kind of architecture, first part copied, and then the second part is scaled and translated. That was quite older than that. There was one architecture called NICE, and this NICE architecture used exactly the same thing without a scaling. The point was that when you use this architecture, they noticed that this, I mean, at the beginning they were super happy because since you have no scaling, essentially that main diagonal of the matrix is going to be all 1, right? And then the determinant is 1, log of determinant is 0. Essentially, you don't have anything to backpropagate over, right? And they were very happy because they are somehow getting rid of that one. And then they saw that, well, it is now they are somehow lacking enough gradient, right? Because you don't have enough gradient to train all of the model. And then they started to add up the linear scaling, but it was not working. This is how they ended up with adding this exponential scaling. So the idea was originally here. And then later on, people extended this idea to generative flow, what we call it CLO. And GLOW was at some point of time quite a thing because it was able to generate very good quality samples. And the idea was essentially the same thing again. The only difference was that they were using the idea of convolution in order to somehow also learn the location of the entries which they are going to combine. So right now in the Real NVP architecture, I told you you just take the first R entries and then you copy it directly, then you process the second entries, right? But there is no need that you do exactly this way, right? So you can select which guys to copy, which guys to process, right? And if you use convolution, you can eventually learn that one as well. And this was the idea that they somehow added to the Real NVP, ending up with GLOW, and this was really something that was working quite good. So the generation quality was quite good. It needed a bit of more computation because this, location is also somehow involved, and then it's a bit of more gradient computations. But at the end of the day, it was worth it because it gave us better results. So this guy, the flow networks are not totally dead. So there are still some other versions of them out there. So these are like up to 2-3 years ago. They were still coming. And yeah, like Flow++, vFlow, and Wavelet Flow. These architectures are all giving, say, close to the state-of-the-art output. Okay? And all of them use the same model, and not exactly the same model, but same design logic as Real NVP is doing. Okay, so any questions? No question? So if you got no question, let me just wrap it up quickly about the flow networks. So flow networks are quite classic. So they are super easy to sample, right? Because you can sample the latent space, and then you can easily pass it through the network to get your output. So this is a very simple thing. So if you want to compare with the two other things we had before, so they are much faster than autoregressive. In the quality, well, they could be the same. Maybe sometimes AR could be a bit better. But in terms of the speed, they are much better, right? And compared to energy-based models, they are definitely both faster and more efficient in terms of sampling, right? Because in energy-based models, you are doing approximate sampling, and you need to use iterative algorithm, whereas here you just do it in one shot, and there is no approximation involved here. So this is with respect to sampling. With respect to training, you essentially end up with such an argument. So you need to be able to compute the gradient of this log det. And this guy could be expensive, but if you just design some specific design like what people did in Real NVP, you can get around this issue, right? But this means that you're going to limit the scope of your design, right? So you should be very careful about your flow network design because you want this log det to be simple, right? So if, again, we want to compare it to what we had before, this is generally more complex than AR, autoregressive models, because you have this log det anyways, and then you either limit your design or you make more computation. But if you want to compare it with energy-based models, it's definitely much easier, right? So energy-based models are like nice guys, very fancy luxury guys, which you can never really compute, right, in the basic form. But of course, they somehow give idea for more efficient processing later. So, any questions? No question? Okay, so if you got no question, this is the end of this chapter. So chapter 3 is over. So basically, we are over with all explicit methods. So any explicit method you find in the literature is somehow either one of them or a mixture of them. Okay? And in these all approaches, we essentially use the distribution. We always work with the distribution. We have the distribution, we compute the likelihood out of it, and we maximize it, right? So any model that we had, it either gives us directly the distribution, or we are able to compute from that model the distribution. This is why I call them explicit methods. So you can have a kind of mixture of these methods. For instance, one of the famous one is AR flow-based models, autoregressive flow-based models. And again, what you can do, I mean, you can imagine what they are doing, right? So they are going to generate autorecursively, so lots of conditional distribution. And when they want to realize every single of those conditional distributions, they are not going to put one network which approximates the distribution. Instead of that, they just do flow, right? They put a flow network, they get the input, and then they just generate the output, right? And then once you get the first one, you're going to take it as the input again to just make the next network condition to that. And again, you use the flow network to generate the next one, and so on, right? So you can combine these ideas together. Not all of them are really promising, like energy-based plus flow doesn't make sense. But, I mean, moral of the story is that whatever you see in the literature is a combination of these ideas, okay? And now, what we want to do now, we want to get into the new chapters, and there we are getting out of this restriction that we really want to know what is data distribution. I mean, if we know, we are happy. If we don't know, we don't care. We just care about generating samples from that distribution. And if you can do it indirectly, that's fine. And this is what GAN, variational autoencoders, and diffusion models are about.